For this problem, we need to find the RMS value of the periodic current shown in our figure. We also need to find the value of the resistor here. And we're going to do this given that the period of the waveform is 50 milliseconds and this graph here. I also pulled this from the notes linked below the like button in section 10.3, the RMS value and power calculations. So to do this, we're working with our integral right here. And that means we're going to be basically finding the area under this curve. So I'm going to break this apart into two different sections because we have two different formulas. So we are going to have this part and then this part that we are going to be looking at. So we're going to write out our equation. This is going to be our IRMS. This is what we're solving for first. We're setting this equal to the square root, and now we're going to look at everything inside of it. We're RT, we know to be 50, so we're just going to have our 1 over 50 in here. And now since we have two equations, we are going to put a bracket in here because we're going to need to factor this in later. But for our first equation, we know that we are going from 0 to 40. Now we need to find a function for this. So we need to write an equation for this entire part right here. Well, what we can do is do the slope formula. We have our y2, which is our 30, minus our y1, which is 0, over x2, which is 40, minus our x1, which is 0, is being multiplied by t. If we do this, we're going to get 3 over 4t. We can plug in values for our t, like 40, and if we do this, we can see that we are going to get 30. So this is the correct formula for this. Plugging this in here, we're going to have 3 over 4 times t, and this is all going to be squared Porter formula, and this is being multiplied by our dt. Now we need the second part, so we're going to have the plus integral from 40 to 50, and now we need an equation for the second part. So for the second part, we're going to do the same thing. We're going to look at the slope. We're going to have our y2, which is 0, minus our y1, which is 30, divided by our x2, 50, minus our x1, which is 40, times t. If we do this, we are going to see that we get a negative 3t. Well, if we plug something in here, like let's say we plug in our 50, we're going to get a negative 150. And that is not going to equal 0. We want it to equal 0 here. So we'll just add our 150 here. We can test this by plugging in our 40. We're going to get 30 from this, which is exactly what we want right here. So this is going to be the equation that we plug into here. Negative 3t plus 150. For the formula, it is going to be squared. And then we're multiplying this by our dt. We have this all under the same square root and all in the bracket. Now to solve this, what I'm going to do is do these separately. This part I'm going to factor out the constants, and for this I'm actually going to do a u sub, so that way we don't have to factor out everything. I'm going to set the u equal to our negative 3t plus 150, and then our d of u is going to be equal to negative 3 times our dt. So basically our du is going to be over a negative 3 and set equal to our dt. Now that we have this, we can plug in the upper and lower bounds. For our upper bound, we are going to have 50. So u is equal to a negative 3 times 50 plus 150, gives us 0. For our lower bound, we're going to do the same thing, where we plug in our 40. 40 times negative 3 is negative 120 plus the 150 is going to give us 30. So these are our new bounds for when we have our u in here. When we rewrite this, we still have 1 over 150 out front, and then we are going to move our constants out after we square it. So we're going to have a 9 over 16. We can also take the integral of this. So inside of here, we're going to have our u cubed over 3, and we know that this is going from 0 to 40, so we're going to have to plug those in for our u, which for here should not be a u, it should be a t. We did not do a u sub in this first part. Now we are going to look at the second part. So we're going to have a plus. Remember, this is all under the same bracket. And this is going to be, we haven't integrated yet. So we're going to still do 40, 50. And this is going from our u squared, like this. And then in our dt, we found our dt to be a du over negative 3. And I'm actually going to move this out here. And we're going to go from here, and we're just going to plug it in here. So now we can take the integral of this, but also move out our negative 3 constant. So when we do this, we're going to have a negative 3 out here, and then in our brackets, we are going to have our u cubed over 3. I also plugged in the wrong bounds right here. Remember, we found these bounds to be 0 and 30. That's what we are changing right here and right here from the 50 and 40. So after we write that, we can have everything written like this, and then write our bounds, and then close it off. That way we still factor in the 150. Now we just need to plug all of this into a calculator. And from here, we are going to get our answer for our part A. That's approximately 17.32 ARMS. And that is the answer for A. Now for B, we are given the periodic waveform dissipation as an average power of 24 kilowatts in our resistor. We are asked what is the value for our resistor. From the notes linked below the like button, we also have this formula here. And this gives us our R. We know our average power to be the 24 kilowatts, and we know our IRMS to be the I that we just found. So all we need to do is rewrite this equation and plug things in. We are going to have our R equal to our P average divided by our IRMS squared. So this is basically going to be our 24 kilo, which is 10 cubed, divided by our IRMS, and our IRMS we found to be 17.32, and this is squared. And if we do this, we are going to get approximately 80. So our answer for part B will be 80 ohms. And that's how you would go about solving for this problem. If you want the notes for this material, they are in the description below the like button, as well as a playlist with more network analysis problems.